to this video, which is slightly late by 6 years almost, but this paper is still incredibly useful, I think, even in 2025. Of course, Dota 2 with large-scale deep reinforcement learning, which was called OpenAI 5, and one of OpenAI's first projects, the first one being the Rubik's Cube solved by a robotic hand, but maybe this is like the second or third that they did like in public. So I'm just going to be going through the paper. I've like highlighted many things. So this is just going to be an explanation of all of the core concepts that you should know. Beginning with the abstract, on April 13, 2019, OpenAI 5 beat the pros, and this game presents novel challenges because of the long time horizons, imperfect information, complex continuous state action spaces, and these are challenges which will become increasingly central to more capable AI systems. Agree. And it leverages RL techniques, but it scales to learn from batches of approximately nearly 2 million frames every 2 seconds. And I guess this can just be said like 1 million frames per second. We developed a distributed training system and tools for continual training, which will allow us to train OpenAI, which allowed them, because they did this for 10 months straight, and they defeated it, demonstrates that self-play reinforcement learning can achieve superhuman performance on a difficult task. And in fact, it's purely self-play reinforcement learning. There's no cold start data or human supervised fine-tuning, which begins the training loop. So very impressive. Let's skip through the introduction, which kind of gives you a background of Go, checkers, chess, AlphaGo, etc. If you want to, then definitely read these ahead. But let's talk about a challenge they faced, which was that the environment and code continually changed as the project progressed. And as I said, like this was run during 10 months. So in order to train without restarting from the beginning after each change, they developed a collection of tools to resume training with minimal loss in performance. There is still a loss in performance though, so do not think that this is trivial. There was a loss, which we will describe, I think, in the second part of this 2-part series. And they called this performance surgery, or at least the act of changing when the environment or code changed. And this was done approximately every 2 weeks, I think around 20 times in total, or how many weeks? So like 4 weeks every 10 months, so more towards 40, sorry. And these tools allowed us to make frequent improvements to our strongest agent with a shorter time than the typical practice of training from scratch would allow, as AI systems tackle large and harder problems. Further investigation of settings with ever-changing environments and iterative development will be critical. So it's quite interesting that once again, they were able to adapt to updates, also changes in the reward function, etc. And I do take that back. Every 2 weeks would be twice per month, and 2 times 10 is around 20. Of course, every month is more than 4 weeks, but this is just an approximation. So Dota 2, if you haven't heard of the game, it's kind of like League of Legends, if I'm not mistaken. It's a 5 versus 5 game, but there's 2 teams of 5. So let's talk about some of the challenges in the game. First of all, it's a long time horizon. Dota 2 games run at 30 frames per second for approximately 45 minutes, but they can last up to 2 hours. And OpenAI 5 selects an action every 4th frame, yielding approximately 20,000 steps per episode. By comparison, chess usually lasts 80 moves and Go 150 moves. So when they say 20,000 steps per episode, an episode is 1 game. And since every 4th frame, if we have 60 frames every 2 seconds, then this means that it's taking 15 actions every 2 seconds, or 7.5 actions every second. And this is going to be restated in the paper. And moving on, they also have a partially observed state. So it's not a perfect information game like chess or Go. Each team in the game can only see the portion of the game state near their units and buildings. The rest of the map is hidden. Strong play requires making inference based on incomplete data and modeling opponent behavior. And there's also a high dimensional action and observation space. So this is kind of themselves making this space because they chose how to represent the action and observation spaces. But I think whatever way it was done, it would have resulted into like a high dimensional space, as they say. So Dota 2 is played on a large map containing 10 heroes, dozens of buildings, dozens of non-player units, and a long tail of game features such as runes, trees, and wards. OpenAI 5 observes 16,000 total values, which are either floats, so like a value from like -infinity to infinity, or categorical values with hundreds of possibilities. So like maybe one categorical value is how many trees do you have in your inventory? Or like, I actually don't know Dota 2 that well, but like, what is your state? Maybe there's like 3 states, like healthy, sick, or sad. So that would be a categorical value. And they discretize the action space on an average time step. Their model chooses among 8,000 to 80,000 actions, depending on the hero. And for comparison, chess requires around 1,000 values per observation, which I choose they choose to add or to explain, which is 6 possible categorical values. I think this might be like if it's a pawn or whatever, but I know like usually how it works with chess is you have like one 8x8 square with all of the white pawns, one 8x8 square with all of the black pawns, one 8x8 square with all of the black knights, and so depending on the number of pieces, I guess there's 10 pieces and then 2 colors, so 20. Maybe it's 20 times 64 would give you the amount. So I'm not sure, is 20 times 64? 20 times 64 is approximately 1,000, but this is just a Fermi calculation. And then with respect to Go, there's 6,000 values per observation, and these are all binary since you just have black and white. But what the interesting aspect of Go is, and I literally searched this up, so in AlphaGo, you're not just storing, so first of all, 19 by 19 is the board size, which gives you 361 tiles. So you would naively think that, well, why is observation 6,000 if there's only 361 tiles and they're all binary? So you can literally just put a 361 one-dimensional array that is row-wise with a 1 if it is black and a 0 if it's white. However, in AlphaGo, it was required, or of course, you need to see what was happening before, or I guess for training this was useful because then the model could see how the game progressed. So what happened is that they had the past 8 turns stored, and I think for some reason this had to be done for every player. So if I'm not mistaken, it was 8 times 2 times 361, and then they also needed to store an entire board which just said whose turn it was. So I may have missed a number here or there, but just know that Go has around 6,000 values. And their system, Dota 2, now we're just moving on, played with two limitations from the regular game. So first of all, they only use 17 heroes. In the normal game, players select before the game from 117 heroes, but they only support 17, I guess, just simplification. And this is another important one. So there's no support for items which allow a player to temporarily control multiple units at the same time. So I think the one that we could probably understand here is like Necronomicon, probably like spawns people from the dead and like has minions that run around. And they removed this to avoid adding technical complexity of enabling agents to control multiple units. Since this is already like, I guess, a multi-agent reinforcement learning setting, if you're like making the multi-agents have their own multi-agents, then this becomes like meta multi-agent reinforcement learning. So let's talk about the training system and playing Dota to use AI. So humans interact with Dota 2 using a keyboard, game, and mouse. They make decisions in real time, etc., etc., etc. Although the Dota 2 engine runs at 30 frames per second, OpenAI 5 only acts on every 4th frame, which is what their time step is called. So each time step, OpenAI 5 receives an observation from the game engine, encoding all the information a human player would see, such as health, position, etc. And OpenAI 5 then returns a discrete action to the game engine, encoding a desired movement, attack, etc. And certain game mechanics were controlled by hand-scripted logic rather than the policy. So it's not an end-to-end deep learning setting. These following actions were human chosen, I guess. So first of all, the order in which humans purchase items and abilities was dictated. The control of the unique courier unit was dictated, and which items heroes keep in reserve. While they think that agents could ultimately perform better if these actions were not scripted, they achieved superhuman performance before doing so. And some properties of the environment were randomized during training, including the heroes in the game and which items the heroes purchased. And now let's get on to the policy, which is what determines the actions taken. And they also describe the neural architecture that's used to control the 5 players. So the pi policy is a function from the observations to a probability distribution over actions, which is the most common formulation of what a policy is, especially in reinforcement learning. And this is parameterized by an RNN with approximately 159 parameters, and it's an LSTM in this case. So the neural network consists of a single layer 4096 unit LSTM, and we'll see the figure. So given a policy, we play games by repeatedly passing the current observation as input and sampling an action from the output distribution at each time step. So we have the LSTM. Let's read the caption first. The simplified OpenAI 5 model architecture. The complex multi-array observation space here is processed into a single vector, I guess right here, in fact, which is then passed through a 4096 unit LSTM. So we have the observation processing to a singular vector, and there also is a hero embedding. So this would be explained here. Each of the 5 heroes in the team is controlled by a replica of this network with nearly identical inputs, each with its own hidden state. So I think this is the hidden state for each hero. And the network takes different actions due to a part of the observations processing. That each hero takes different actions due to a part of the observation processing output, indicating which of the 5 heroes being controlled. And the LSTM composes 84% of the model's total parameter count. So the other parameters would be in the value function, the action heads, which determine the policy, or which determine the action, in fact. So we have this large LSTM here. Tied weights, there's 5. So this is to say that these weights are shared among the heroes, and therefore the only weights that I guess are hero specific or hero unique would be this hero embedding. So we have observation processing, which gives us the ground truth observation plus the hero embedding, which tells the LSTM like which person should act. If this wasn't here, then I believe naively every agent would take the same action. But because of this, we have the action per agent, and then based on the LSTM output, we get a value function, which is used to train using advantage estimation, which I think is, it is discussed later on, and then the actual action itself. So separate replicas of the same policy function with identical parameters pi are used to control each of the 5 heroes on the team. And I think this is what is meant by here with the tied weights. And because visible information and fog of war, so fog of war being area that is visible to players due to proximity of friendly units, I think fog of war is usually defined in the opposite, say it's like area that is not visible because you're not in proximity to it. But anyways, because visible information is shared across a team in Dota 2, the observations are nearly identical for each hero. So I did not know this. I thought that like the heroes would have their own observation space, but apparently not. And now let's talk about like the vision and observation in particular. So they don't use pixels. They take the information and get a semantic observation space by putting it into a data array. So let's jump right here. OpenAI 5 uses this semantic observation space for 2 reasons. First, because our goal is to study strategic planning and high-level decision-making rather than focus on visual processing. So you can imagine that if the agent had to essentially take in the however large the resolution is in pixels and do this end to end as a human would, take the instance of the pixels and then provide an output with the keyboard and mouse, then it is like a well-motivated problem, but so much computation and work would be dedicated toward visual processing that whereas like the LSTM would be 84% here, I think it would be like much less if you had to actually process the input completely as a model. So they just want to focus only on strategy. And secondly, it is infeasible for us to render each frame to pixel in all training games. This would multiply the computation resources required for the project manyfold. So I think they're saying that if they actually had to render, I think this is because they're doing this on a headless server, most likely, which means that the game is running in the engine when the training happens, but there's no actual graphics, because why would you need graphics if it's an AI playing? Like the AI doesn't need to see the characters moving around if it just gets the array observations. So if they did have to use the pixels, then what this means is that they would have to render the game, which of course, GPUs were literally made specifically for rendering games, and GPUs are very beefy compute units. So you can imagine that you have to like dedicate an entire cluster of GPUs just to rendering the game. Whereas when you have it on a headless server, this is not required. So where were we? We're here. Although these discrepancies exist, which is to say that humans observe the game, whereas OpenAI 5 just gets this semantic observation space, we do not believe they introduce significant bias when benchmarking against human players. So on what basis they do not believe that this is the case, I don't know, because it's not fundamentally the same. But I think that the best reasoning is that they just want to focus on strategy, which makes sense to me. To allow the 5 networks to choose different actions, oh, this is the same thing that we've read, LSTM receives an extra input from the observation processing, which is that. Sorry for repeating myself so many times. And because of the expansive nature of the problem and the size and expense, not expanse, of each experiment, it was not practical to investigate all the details of the policy and training system. Many details, even some large ones, were set for historical reasons or on the basis of preliminary investigations without full ablations. All they're saying here is that the space of parameters and different design and engineering choices is so large that they simply chose ones probably by default and just trusted that as long as you can give the compute and the data, it will not make a substantial difference on like minute changes in the parameters. And of course, these are also world-class engineers, so they know what they're doing. All right, let's talk about the policy optimization. I highlighted everything here, so I guess it's important. Our goal is to find a policy which maximizes the probability of winning the game against professional human experts. And this means that they maximize a reward function, which includes additional signals such as characters dying, collecting resources, etc. So that what they're saying is that the reward is not just did you win or did you lose. There are intermediate rewards as well, which is good because a big problem in reinforcement learning is sparse rewards and the credit assignment problem, which is to say, like, this is most easily explained in chess. If you win a game in chess and your only reward signal comes from the +1 or -1 from the very end of the game, well, how do you know which of those 80 moves contributed to the win? Whereas if you have intermediate moves, like, did you not die because there's 5 players, so if somebody dies, that doesn't mean you lose. Then if you prevented yourself from dying, then that's a signal that you were good, okay? Or I think this is rather, if you did die, then it's a signal that you were bad, so you get a negative reward. We also apply several techniques to exploit the zero-sum multiplayer structure of the problem when computing the reward function. For example, we symmetrize rewards by subtracting the reward earned by the opposing team, okay? We discuss the details. So they discuss a lot of details in the appendix. We constructed the reward function once at the start of the project based on that team members familiar with the game. Although we made minor tweaks when game version changed, we found that our initial choice of what to reward worked fairly well. The presence of these additional signals was important for successful training. So they're saying is that OpenAI is a bunch of nerds, and in the not in the appendix, but in the recognition section where they thank everybody, they thank a lot of their team members for like playing the game and explaining like what was happening, because I guess a lot of people in OpenAI are also Dota 2 players. So we talked about PPO, proximal policy optimization, made by John Schulman, who was also at OpenAI, a variant of advantage actor critic. So this is the case where you have an advantage policy and an actor policy in reinforcement learning, where an actor policy and a critic policy, where the actor is the one which will act in the environment, and the critic is the value function. So the actor is the policy, the critic is the value function. The optimization algorithm uses generalized advantage estimation, GAE, which I didn't look into this, but it's just a standard advantage-based variance reduction technique to stabilize and accelerate training. So RL is very brittle, so anything that can stabilize training would not be bad. We train a LSTM block that feeds into separate fully connected layers producing policy and value function outputs. And I'm going to repeat myself for the 10th time, but that's these two heads here, the value function and the actor head. Okay, where were we now? Here. The training system is represented in figure 2, which I think, oh no, we'll see that later. We train our policy using collected self-play experience from playing Dota 2. So they have an experience buffer. A central pool of optimizer GPUs receives game data and stores it asynchronously. So this means off policy. We're not training on the data as we play, but rather it's in local buffers called experience buffers. Each optimizer GPU computes gradients using mini batches sampled randomly from its experience buffer, and gradients are averaged across the pool using NCCL2 all reduce. So I always forget what this means, but it's just a distributed communication primitive library, which is used for NVIDIA GPUs, or they're using the Google Cloud for this. So maybe it was actually GPUs, but all reduce is just used to synchronize weights. And in this way, the effective batch size is the batch size on each GPU, which means 120 samples with 16 time steps, multiplied by the number of GPUs up to 1,536 at the peak, for a total batch size of 2.9 million time steps, each with 5 hero policy replicas. So I think what they're saying here is that, first of all, they do 120 times 16 times 1536, and this gives you approximately 3 million, and it's repeated across 5 hero policies, but they're just redundant, I assume. And then they use Atom Optimizer, so no surprise, using truncated backpropagation through time. And I looked into this. It's essentially a LSTM version, I guess an LSTM modified version of Atom, which because LSTM is recurrent, we have to have this temporal aspect, and it's done over samples of 16 time steps. And remember, one time step is 4 frames. So 16 times 4 is 64, which means that there are 64 time steps per optimizer step, which is approximately 2 seconds of gameplay, because there are 30 frames in a second. So that's why they said in the very beginning, I think 2 million per every 2 seconds, even though it's closer to 3 million. So that's strange. Moving on, gradients are additionally clipped per parameter to be within plus or minus 5 divided by the square root of v, and v is the running estimate of the second moment of the unclipped gradient. This may sound like Chinese to you, but this is the adaptive learning rate, or the second moment. Yeah, it's the second moment, which is the v value in the Atom calculation. I know there's a third word for this this value, but all you need to know is that this is what is in the denominator of the Atom Optimizer equation, which is essentially saying that it is scaling the gradient update by the magnitude of the gradients, like scaling it by dividing by it. It's not like increasing it. Usually it's like dividing, so the gradient update becomes smaller, in fact. And this is unclipped, which is worth noting. It's not clipped. Every 32 gradient steps, the optimizers publish a new version of the parameters to a central Redis storage. So Redis is just like a NoSQL cache database. This is the high-level understanding of what that I have of what it is. And this is called the controller. The controller also stores all metadata about the state of the system for stopping and restarting training runs. Okay, rollout worker machines run self-play games. So these are the actual actors, or they're not the actors, but they're the ones that are calling the actors to act for them. Now, I'll explain that in this diagram here. They run these games at approximately half real time, because we found that we could run slightly more than twice as many games in parallel at this speed, increasing total throughput, which is quite compelling. Like, I'm not sure how the details of this are, but they do explain it in Appendix K if you're interested. They play the latest policy against itself for 80% of the games and play against older policies for 20% of the games. So is that a 4-to-1 ratio? For detail of opponent sampling, okay, the rollout machines run the game engine but not the policy. Okay, I was right about this. They run the gaming engine but not the policy. They communicate with a separate pool of GPU machines which run forward passes in larger batches of approximately 60. These machines frequently pull the controller to gather the newest parameters. So to summarize, the GPU machines get the parameters from the controller, and they run the policy for the rollout machines, and they do this in large batches of 60, such that we don't have like each controller, I guess, doing a single batch forward pass to calculate what action it should do. And you can see that this is so complex that if we also added the pixels and rendering and all of the visual stimuli, then that would just make this project intractable. At least that's what I think. So this is worth noting. Another thing is that they considered different algorithms for policy gradient methods, Q-learning, and evolutionary strategies, but they just remained with proximal policy optimization since it was the first one to show initial learning progress. Okay, so we talked about it in text. I guess we're going to talk about it in text one more time in this overview and then map it to this diagram. So our training system contains 4 primary types of machines. Rollout run the Dota 2 game on CPUs. So right here, bunch of CPUs doing work on the game. And each rollout worker is viewed as a control code has Python and converts the state from the numerical observation. Converts the state to numerical observation, which they define in their semantic space, and computes the reward and the general advantage estimate, if I'm not mistaken. And then also it runs on Docker the game itself with Lua, which is like a scripting API, and it's also used in many other games such as Factorial. And then I'm not sure what a gRPC server is, but this must communicate with, I guess, the workers. And this is the rollout stage. They communicate in a type loop with forward pass GPUs, which are here, which sample actions from the policy given the current observation. And rollouts send their data to optimizer GPUs on the right here, which perform gradient updates. The optimizers publish the parameter versions to storage in the controller, which is here, which was a Redis database, if we remember. And the forward pass GPUs occasionally pull the latest parameter version from the controller. I think it was every 32 time steps, if I'm not mistaken. And where are we now? Machine numbers are for the, I didn't understand what this meant, but if somebody knows, please tell me. Machine numbers are for the rerun experiment described in section 4.2. OpenAI 5's numbers fluctuated between this scale and approximately 3x larger. So like this makes sense. I guess they talked about 15,000, yeah, there you go. There was up to 1,536 GPUs. I guess the average might have been 512. And that is just amazing for me to begin, because I don't know how you like have a variable algorithm that can just scale from 1x to 3x the number of compute. Very impressive engineering. And then if somebody knows what they're talking about here in the first clause of the sentence, then please do let me know. Rollout machines send data asynchronously from games that are in progress. So they send the data here asynchronously, 256 samples every minute. Like these are all just numbers that I have no idea how they got, but it's just once again really impressive. The all reduced was for the GPU gradient, not gradient, but weight synchronizing, if we remember. And instead of waiting for an entire game to finish before publishing data for optimization. So another method would be to wait every 45 minutes and then publish the data. They explain why this is like a totally bad idea, so I won't spoil it for you. And there's also a figure here. Because we use GAE with lambda equals to 0.95, the general advantage estimate rewards need to be smoothed over a number of time steps, which is greater than 1 divided by lambda, which is equal to 20, because 1 divided by 0.95. I think they messed this up. Okay, I just found a typo in this paper. Wow. Okay, this is supposed to be 1 divided by 1 minus lambda. I can't believe this. You guys just literally witnessed me find a typo live in this paper. Unless I'm mistaken, but I don't think so. Because the formula for discounted reward is literally, as I have it here, 1 over 1 minus lambda. And in any case, what we have here is 1 over 1 minus 0.95, which gives you 1 divided by 0.05, which is the same as 1 times 20, which gives you 20. And let's explain why this is the case. Like, what does this even say? So generalized advantage estimation is a method for computing the advantage function in policy gradient reinforcement learning. It uses a discount factor lambda to control how much to weight short-term versus long-term rewards. So it's just a reward discounter. And this means with 0.95 that you carry, whatever. 0.95 is just like standard value, which balances both long-term and current reward. But what does 1 over lambda or 1 over 1 minus lambda mean? It means that the effective smoothing timescale for the generalized advantage estimate reward is approximately 1 over 1 minus lambda. So this gives us 20 time steps. So the advantage estimation becomes stable and meaningful only when you average or smooth rewards over at least 20 steps. So in an intuitive sense, what we're doing here, first of all, 1 divided by 1 minus lambda is the sum of the infinite geometric series 1 plus lambda squared plus lambda cubed, where lambda is less than 1 and greater than 0. This is very important in order to converge the series. And why we have convergence, or sorry, this infinite geometric sum is just the sum of the rewards all the way to the last time step, okay? And what I want to get at here is that eventually, or since we have the sum equal to 20, it's as if we had 20 full value time steps. Because if you literally don't discount the reward, then your reward will be infinite in expectation, but of course at a certain point it would stop, but you're valuing current rewards the same as future rewards. But since we do discount them, it eventually converges to 20 effective full value estimates. So you need at least 20 samples or steps in order for this to be meaningful. And they say that it actually should be larger than 20. So they use 256 time steps, which causes relatively little loss. The entire system runs on our custom distributed training platform called Rapid5, which unfortunately I tried to look is not open source, running on GCP. And they use the distributed communication primitives from Block Sparse library for fast GPU training. So I guess this is likely open source. I didn't check that. And check the appendix for hyperparameters. If you didn't understand what I was talking about regarding the general advantage estimate, please read this again or spar with Claude, because that's what I did. And that's all for the first episode. Hopefully we can get this done in 2, and I hope you have a good day.